Welcome to Grade 10, Unit 6, Polygons. The objectives for this lesson are to review circle, diameter, radius, circumference, types of arc, inscribed and circumscribed angles, to review theorems involving circles, and to solve problems involving circle theorems. Circles and parts of circles. A circle is a 2D shape where all the points are the same distance from a point called the centre. The circumference is the distance all the way around a circle. A radius is a line segment drawn from the centre of the circle to the circumference. The diameter is a line segment that connects 2 points on the circle and passes through the centre. A chord is a line segment that connects 2 points on the circle. It doesn't have to pass through the centre. An arc is a part of a circle. For example, this arc here. It goes part way around the circle. Circles that share the same centre are called concentric circles. An arc that measures half the circumference of a circle is called a semicircle. So this here is a semicircle, and it measures 180 degrees because it's half of 360 degrees. An arc that measures less than a semicircle is called a minor arc. For example, this one here. An arc that measures more than a semicircle is called a major arc. Tangent and secant. A tangent line is a line that touches a circle at exactly 1 point. For example, this black line here. A secant line is a line that intersects a circle at exactly 2 points, like this red line here, which intersects here and here. This green line does not intersect or touch the circle at all. It stays outside the circle. A tangent always meets the radius at right angles. So if this is a tangent and this is a radius, then this angle is always 90 degrees. Arcs and inscribed angles. PQ refers to the minor arc. PRQ refers to the major arc, going all the way around the edge through the point R. The angle POQ, this angle here, intercepts the arc PQ. The arc PQ subtends the angle POQ. This angle here, POQ, is the central angle, where the vertex is at the centre and the radii are the sides. The measure of a central angle and the arc it intercepts are equal. In other words, the measure of angle POQ is equal to the measure of the minor arc PQ. In this diagram, this is an inscribed angle. The vertex is on the circle, and the chords are the sides. Inscribed angle. Theorem 6.9. The measure of an angle inscribed in a circle is half the measure of the arc subtending it. Case 1, where the line goes through the centre O. Here's the proof of this theorem for case 1. Here's the arc, and here's the inscribed angle, theta. If we draw in a line from O to P, then we know that these two lines, OP and OA, are equal in length because they are both radii. So we know we have an isosceles triangle, and angle OPA is also theta. Therefore, this angle is 180 minus 2 theta, which means that this angle is 180 minus 180 minus 2 theta, because we have a straight line. And that simplifies to 180 minus 180 plus 2 theta, which is 2 theta. So the measure of the arc PR is 2 theta, because it's equal to the angle at the centre, which means that the measure of the arc PR is twice as big as the original angle theta. Or the other way round, the measure of angle PAR is half of the measure of the arc PR. Case 2, where the two lines are chords going around the centre. Again, here's the arc PR and here's the angle that we're working with. The proof in this case: first of all, we'll draw a line from A through the centre to meet the circumference at the point C. Then we know from before that if the measure of this arc is theta, then the measure of this angle is half theta. So the measure of angle PAC is a half of the measure of the arc PC. And on the other side, this is the arc CR, which we'll call beta, and we know that this angle here is beta over 2. So the measure of angle CAR is half of the measure of the arc CR. If we put all of that together, then the measure of the arc PCR all the way round is theta plus beta, and the measure of angle PAR, this angle here, is theta over 2 plus beta over 2, which is theta plus beta over 2, which is half of the measure of the arc PCR. Case 3, to the side of O. So in this case, here's our arc and here's our angle. Again, we'll draw a line from A through the centre, which meets the circumference at the point C. From case 1, we know that if the arc CP has a measure of theta, then the angle PAC has a measure of half theta, because the angle PAC is half of the measure of the arc PRC. Also, if we take this smaller shape, the measure of the angle CAR is beta over 2, because it's half of the measure of the arc CR. Therefore, the measure of the arc PR, which is the part that we're interested in, is equal to theta, all the way round, minus beta. And the measure of angle PAR, which is the angle that we care about, is equal to theta over 2, all the way across, minus beta over 2, which is theta minus beta over 2, which is half of the measure of the arc PR. Example: if the measure of the arc RP is 70 degrees, what will be the measure of angle RAP? The measure of RAP, this angle here, is going to be half of the measure of the arc, so half of 70 degrees, which is 35 degrees. And we can conclude that the angle inscribed in a minor arc is always an obtuse angle, greater than 90 degrees. And we can conclude that the angle inscribed in a major arc is always an acute angle. The angle inscribed in a semicircle is a right angle. It's exactly equal to 90 degrees. Example: AB is the diameter of the circle below. If BC is 6 cm and AB is 10 cm, find the exact length of AC. We can use the fact that the angle inscribed in a semicircle is always 90 degrees, and that means that we have a right-angled triangle. With a right-angled triangle, we can use Pythagoras' theorem. A squared plus B squared equals C squared. So we know that A squared plus 6 squared equals 10 squared. So A squared plus 36 equals 100. A squared equals 64. So A is 8. The length AC is 8 centimeters. inscribed angles subtended by the same arc are congruent. So here's an arc here, and we're going to prove that all the angles subtended by this arc are the same size. Here's the proof. Draw in an angle subtended by this arc. We know that the measure of the angle is half the measure of the arc. So if we call the angle theta, then the measure of the arc is 2 theta. Now, if we draw another angle also subtended by the same arc, then the measure of this angle must be half of 2 theta. So this angle must be theta. And if we draw in another one, this one must also be theta. And we can see that all the angles subtended by this arc have the same size. They are all equal to theta. Theorem 6.10. Two parallel lines intercept congruent arcs on the same circle. We're going to start with the proof for case 1, where the two parallel lines are tangents. In this case, if we draw a line from C to D, then we know that a tangent meets a radius at 90 degrees. So each of these angles are right angles. This is a semicircle, so the measure of this arc is 180 degrees. And this is a semicircle, the measure of this arc is 180 degrees. So the two arcs are congruent. Case 2, where we have two secants that are parallel. A secant intercepts a circle at exactly 2 points. This time, let's draw a line from C to D, and then we know that because these lines are parallel, these two angles are alternate, so they are equal. Then we know that the arc subtending an angle is equal to twice the angle. So the measure of this arc is 2 theta, because it's twice as big as this angle, and the measure of this arc is 2 theta, because it's twice as big as this angle. So the measures of the two arcs are equal. Case 3. One tangent at the top here, and one secant at the bottom here. This time, we'll draw a line through the centre, and we'll mark on this point C on the circumference. As before, the tangent meets the radius at 90 degrees. And then because these lines are parallel, this angle and this angle are alternate. So this one is also 90 degrees. If we call the measure of this arc theta, then the measure of this arc must also be theta. And the measure of this arc must be 180 minus theta, and the measure of this arc must be 180 minus theta. So the measures of the two arcs are equal. Theorem 6.11. An angle formed by a tangent and a chord drawn from the point of tangency is measured by half the arc that it intercepts. In other words, this angle here is equal to half of the measure of this arc here. To prove this, we'll draw in a parallel line here, and we'll draw in a line through the centre. The line through the centre meets the tangent and this line at 90 degrees. Then this angle and this angle are alternate, so they are equal. And the measure of this arc is twice the measure of this angle. So the measure of this arc is 2 theta. And therefore the measure of this arc is also 2 theta by the previous theorem. And we can conclude that the measure of this angle is half of the measure of the arc that it intercepts. Theorem 6.12. The measure of an angle formed by two chords intersecting inside a circle is half the sum of the measures of the arc subtending the angle and its vertically opposite angle. Here's a diagram. Here are two chords intersecting inside a circle. They intersect at the point F. The theorem says that the measure of this angle, alpha, is equal to half of the sum of the measure of this arc, which subtends the angle, and this arc, which subtends the vertically opposite angle. In other words, alpha equals a half of theta plus beta. If two chords intersect inside a circle, the product of the segments of one is equal to the product of the segments of the other. So that means that CE multiplied by ED is equal to AE multiplied by EB. Example: chord AB is 12.3 centimeters, EB is 2.7 centimeters, and DE is 10.6 centimeters. Find the length of EC correct to 1 decimal place. To do this, we know that AB is 12.3 and EB is 2.7. So AE is 12.3 minus 2.7, which is 9.6. We also know that DE is 10.6. So using the theorem, CE times ED equals AE times EB, we know that CE times 10.6 equals 9.6 times 2.7. So CE equals 9.6 times 2.7 over 10.6, which is 2.4 centimeters. Example: in circle O, the measure of angle SPR is 44 degrees, and the measure of angle OSP is 32 degrees. Find X and Y. First of all, we know that the measure of this arc must be 88 degrees because it must be twice 44 degrees. So the measure of the angle at the centre is also 88 degrees. This is an isosceles triangle because these two sides are both radii of the circle. So these two angles are equal. So we know that theta must be equal to 180 minus 88 over 2, which is 46 degrees. So this angle here is 32 plus 46, which is 78 degrees. This is a cyclic quadrilateral because all four vertices are on the circumference of the circle. In a cyclic quadrilateral, opposite angles add up to 180 degrees. So X is 180 minus 78, which is 102 degrees. We also have another quadrilateral here. It's not a cyclic quadrilateral, but we can still use the fact that angles inside a quadrilateral add up to 360 degrees. This angle here is equal to 360 minus 88, which is 272 degrees. So y plus 32 plus 44 plus 272 equals 360. So y equals 12 degrees. And this is what we were trying to prove. Lines intersecting outside a circle. Theorem 6.13. The measure of the angle formed by the lines of two chords intersecting outside a circle is half the difference of the measure of the arcs they intercept. So let's draw this on. Here's two chords intersecting outside a circle. The theorem says that the measure of this angle is equal to half of the difference between these two arcs. So the measure of this angle is half of beta minus theta. Theorem 6.14. The measure of the angle formed by a tangent and a secant drawn to a circle from a point outside the circle is equal to 1/2 the difference of the measures of the intercepted arcs. So what we're trying to prove is that the measure of this angle here is equal to half of beta minus theta. Example. In the figure below, prove that PQ times PS equals PR times PT. We'll prove this using similar triangles. If we draw in these lines from Q to T and R to S, then we know that these two angles are equal because they are both subtended by this arc, and we know that these two angles are equal because they are both subtended by this arc. So therefore, this angle and this angle are equal because of this straight line and this straight line. So triangle PSR, which is this one here, is similar to triangle PTQ, which is this one here, by angle, angle, angle. So the ratio PS, this long side, over PT, this long side, is equal to the ratio PR, this short side, over PQ, this short side. So PS times PQ equals PR times PT. Theorem 6.15. If a secant and a tangent are drawn from a point outside a circle, then the square of the length of the tangent is equal to the product of the lengths of the line segment. So PR squared equals PQ times PS. Simple polygons. A polygon has to be a two-dimensional shape, so this is not a polygon. It's made of line segments, so this is not a polygon because this has a curve. It has to be closed, so these are not polygons. And none of the sides cross each other, so this is not a polygon. These four shapes here are two-dimensional, closed shapes made of line segments that do not cross each other, so these are all polygons. Regular polygons. A polygon with four equal sides is called equilateral. A polygon with four equal angles is called equiangular. An equilateral and equiangular polygon is called a regular polygon. For example, a square has four sides and four angles the same. An equilateral triangle has three sides and three angles the same. And a regular pentagon has 5 sides and 5 angles the same. Circumscribed circle. Here's a pentagon. This circle is circumscribed around the pentagon. A circumscribed circle is a circle that passes through all the vertices of a plane figure and contains the entire figure in its interior. So this green circle passes through all 5 vertices of the pentagon and contains the entire pentagon in its interior. Inscribed circle. Here's a pentagon, and here are some circles. An inscribed circle is the largest possible circle that can be drawn on the inside of a plane figure. So this circle is inscribed in the pentagon. It's the largest possible circle that can be drawn inside the pentagon. Each side of the polygon must be tangent to the circle. So each of these 5 sides is a tangent to the circle and touches the circle exactly once. All triangles and regular polygons have circumscribed and inscribed circles. Formula for the area of a triangle. In this example, we're going to prove that the area of a triangle is half the product of 2 sides times the sine of the included angle. To prove this, we'll start with a diagram. Here are 2 sides with length A and B, and here's the included angle theta. If we draw in the height of the triangle H, which meets the base at 90 degrees, then we know that the area of a triangle is half times base times height, so half BH. What we need to do now is rewrite H in terms of A, B and theta. We know that sine theta is opposite over hypotenuse, which is H over A. So we can rewrite H as A times sine theta. So the area of the triangle is a half times A times B times sine theta. Perimeter and area of regular polygons. In this example, we'll draw a pentagon with 5 sides, but we're going to assume that our regular polygon in general has n sides. Let's divide our polygon into 5 triangles, or n triangles in general. Each of these triangles is exactly the same as each of the other triangles, because the polygon is regular. So this angle here is the same as all of these other angles. So that means that angle AOB is equal to 360 divided by n, because there are n angles at the centre. Half of this angle here we'll label as theta, and we'll work with this right-angled triangle OAD. Theta is half of 360 over n, so theta is equal to 180 over n. If we call the radius r, then by trigonometry we know that sine theta is opposite over hypotenuse, which is the length dA over r. So that means that the length dA is equal to r times sine theta. Therefore, the side AB of the pentagon, or the regular polygon, is equal to 2 times r times sine theta. And this means that we can find the perimeter of the regular polygon, because the perimeter is n lots of this length here. So it's 2nr sine theta. In other words, the perimeter is 2nr sine 180 over n. We can also find the area in a similar way. We already know that the size of this angle is 360 over n. So to find the area of the triangle, we can use the formula that we have just recently proven, that the area of a triangle is equal to half of the product of two sides times the sine of the included angle. So in this case, the area of this triangle is equal to half of the product of r and r times sine of this included angle, which is half times r times sine of 360 over n, or half r squared sine 360 over n. Therefore, the area of the n-sided polygon is a half nr squared sine 360 over n. Example: find the area and perimeter of a regular 9-sided polygon with radius of 5 units. To do this, we can use the perimeter and area formulas that we've just worked out. The perimeter is 2nr sine 180 over n. In this case, n is 9 because the polygon has 9 sides, and r is 5 because the radius is 5. So the perimeter is 2 times 9 times 5 times sine of 180 over 9, which is 90 times sine 20, which is 30.78 units. The area is a half n r squared sine 360 over n, which is a half times 9 times 5 squared times sine of 360 over 9, which is a half times 9 times 25 times sine 40, which is 72.31 square units. Is an angle whose vertex lies on the circle and whose sides are chords of the circle, like this one here. The measure of an angle inscribed in a circle is half the measure of the arc subtending it. The angle inscribed in a semicircle is a right angle. Same arc. If two inscribed angles of a circle intercept the same arc, then the angles are congruent. If one chord is a perpendicular bisector of another chord, then the first chord is a diameter. Cyclic quadrilaterals. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. If two chords intersect on the interior of a circle, then the measure of each angle is half the sum of the measures of the arcs intercepted by the angle and its vertical angle, so theta is a half of alpha plus beta, and also the product of the lengths of the segments of one chord is equal to the product of the lengths of the segment of the other chord. So A times B equals C times D. If two tangents meet at a point outside the circle, their lengths are equal. If two secants meet at a point outside the circle, then A times A plus B equals C times C plus D. If two chords, tangents and/or secants, intersect in the exterior of a circle, then the measure of the angle formed is 1/2 the difference of the measures of the intercepted arcs. So theta is a half of beta minus alpha. Tangent and chord. If a tangent and a chord intersect at a point on a circle, then the measure of each angle formed is 1/2 the measure of its intersected arc. So in this case, theta is 1/2 of the measure of this arc here.